Last time you discovered the relationship between basis vector and basis normal. It was Kronecker delta. In this video, let's try to find the normal transformation based on those relationships and linearity. When the basis changes, how is the normal transformed? The epsilon1' becomes like this. The epsilon1' lines are not perpendicular to the E1'. Those lines are parallel to the E2'. E2' has 0 epsilon1 components. This means epsilon1' E2' is equal to 0. The epsilon2' is like this. Again, the epsilon2' lines are not perpendicular to the E2'. These lines are parallel to the E1'. E1' has 0 epsilon2 components. This means epsilon2' E1' is equal to 0. For the sake of simplicity, you define the width of the magnitude of epsilon1' function to 1. You also define the magnitude of the epsilon2' to 1. Therefore, the normal transform should hold the Kronecker delta. That's how you transform the normal. A basis change is a coordinate system change. You try to visualize the relationship between coordinate system change and normal transformation. Here is the standard basis. Now you perform your basis change. The coordinate system is transformed and forms skew coordinates. Let's overlay the epsilon1. You found it is aligned to a coordinate. Epsilon2 is also aligned to a coordinate. This is not a proof, but you feel this is more natural than the perpendicular normal. Actually, Kronecker delta condition and linearity can derive the normal transform. So let's review the linearity first. 1. Additivity. For a vector, you can add vectors first, or you can add them after multiplying the scalar value c. A normal is the same. You can first evaluate the vector and then add, or first add the normal and then evaluate the vector. Both are equal. 2. Homogeneity. For vectors, you can multiply later or first. For normals as well, you can change the order of multiplication. First, a basis vector change uses the forward matrix F. The new basis EI' is a linear combination of the old basis EI. You already explained why this is to 1 instead of 1, 2. Second, the relationship between the basis vector and the basis normal is the Kronecker delta function. Third, the basis normal changes, but you only assume it is a linear combination of the old basis normal. Your normal transformation matrix is Q. So what is Q? What you want to know is the epsilon I' Ej'. Say I is equal to 1 and j is equal to 1. This is epsilon1'. And this is E1'. Distribute the basis vector. Distribute the parameter using linearity. The same as the Q1 to epsilon2. Using linearity, you can pull out the coefficients f. Use the Kronecker delta condition. These are I is equal to j, so 1. Then I can remove them. These values are I is not equal to j, so 0. These zeros are a great property of a basis. You don't need to think about it, so the remaining terms are those. The same discussion applies to the rest of the cases. You also know the relationship between the new basis normal and new basis vector. The Kronecker delta. These are 1s and these are zeros. Now we know 4 unknowns Q and 4 equations, so you can solve for Q. However, wait, you are familiar with these highly regular patterns. Here is the patterns. The inner suffix of the first terms here is 1. The inner suffix of the second terms here is 2. The epsilon1 suffixes are here, The epsilon2's suffixes are here. The e1's suffixes are here. The e2' suffix are here. What is this pattern? This pattern is the matrix multiplication pattern. The multiplication of Q and F follows. Let's compare the components. You see that each component of the matrix corresponds with each relationship, and they are Kronecker delta. Therefore, this matrix is the identity matrix. You now know what is Q. Q is the inverse of F, which means Q is B. Finally, you found the normal transformation matrix, that is B, the inverse of F. So far, you think about the normal transformation in the two-dimensional case. Expanding this to the three-dimensional case is not difficult. Actually, you can expand this to the n-dimensional case. A new basis vector can be written as a linear combination of the old basis. The coefficient is the components of the forward matrix F. The basis should have the Kronecker delta relationships. A new basis normal can also be written by a linear combination of the old basis normal. The unknown coefficient is the components of a matrix Q. Let's compute the new basis. Epsilon I dash is here, substitute with sigma qik epsilon k. Ej dash is here, but we need to change the indexes, not to confuse epsilon I dash. Substitute with sigma flj el. Using linearity, we can rearrange the terms. This epsilon k el is Kronecker's delta. Because of Kronecker's delta, when L is not equals to k, the value is 0. We can rename the index L to index k since all L that are not equal to k will be removed. Thus flj becomes fkj. In the same way as before, most of the terms of this summation becomes 0 except k is equal to L. Thus, we can only use k. Then, delta Lk becomes delta Kk, and delta Kk is always 1, so we can remove delta Kk. The left-hand side of this equation is also the Kronecker's delta. We also know this summation is the component of matrix Qf. When the component of a matrix is the Kronecker's delta, it is an identity matrix. Therefore, Qf equals I, then Q is the inverse of F. Finally, Q is B. We found the normal transformation matrix is B in n-dimensional case. Let's summarize the transformation. We have basis vector change and its components change. You started the basis vector change. This transformation matrix is F, the forward matrix. The backward matrix B is from new to old and the inverse of F. You see the vector components use B for the old to new, so the components behave as the inverse of the basis vector change. You see that when the universe expands, the components shrink. You find that the basis normal change is the inverse of the basis vector change, so from old to new, it uses backward matrix B. For new to old, it uses forward matrix F. You find the normal components change uses the inverse matrix of basis normal change. In the notation, when the change followed the forward matrix, you used the subscript. But if the change followed the backward matrix, you use the superscript. It is a standard mathematics convention. The basis normal change followed the backward matrix, thus the basis normal change should use the superscript. You feel a bit happy because you find the simple and symmetric relationships. But you still have 3 remaining questions. 1. Some computer graphics textbooks and Wikipedia say that the normal transformation is the transpose of the inverse of B, not just an inverse. You have already seen that the normal is a column vector in the computer graphics world. Also, you almost always live in the orthonormal standard basis world. In that world with the normal function, you can make a row vector by transposing the vector. Therefore, a transpose is needed. You see that this transpose is artificial. This is broken on a non-orthonormal basis, but many graphic systems use an orthonormal basis. The second question is, why does homogeneous scaling work on just B? The homogeneous scaling matrix is SI. What is the inverse of a SI? It is 1 over SI. In the computer graphics world, a normal vector is normalized. That means the transform matrix is just I. Therefore, normalization makes this work. The part 1 video shows non-homogeneous scaling breaks this. The third question is, why does rotation work on just B? What is the transpose of inverse of a rotation matrix R? A rotation matrix has a special property. The inverse of a rotation matrix R is the transpose of R. Substitute R inverse with the R transpose. The transpose of the transpose of R is just equal to R. Therefore, it isn't actually B, it is the transpose of the inverse of B. But just B looks work. You understand a bit more about normals. Actually, the question of this video could be, what is normal? A normal is a function, not a vector. It is not a column vector. Mathematician calls this a covector. Components of a covector follows the forward matrix F. A normal is also called a pseudovector, since it follows the right-hand rule. Our vector is the pencil model, thus it is physical. However, choosing left or right is a human factor, thus it is not a physical vector like our pencil model. Mathematicians call your vector a contravector because the component of the vector don't follow F, but F inverse. The change contradicts the forwarding matrix. A normal is a covector which follows the inverse matrix of the contravector change. Thank you for coming on this personal journey with me about transforming normals. As you see, I made many mistakes and sometimes don't walk toward the problem. It was not a straightforward way to understand my question. Why is the normal transform the transpose of the inverse? For further exploration, the mathematics of vector spaces and tensor algebra are a great place to start. I will continue to explore more. I basically live in the Euclidean space with the standard basis. In this world, the Pythagorean theorem always worked. Transforming normals and basis changes broke the Pythagorean theorem. The Pythagorean theorem is just a special case. In my old world, I didn't need to care that a vector is a column vector or a row vector. I didn't need a metric tensor since it is always an identity. I don't need dual space and therefore I didn't understand my university vector space course. On the Wikipedia page, my discoveries in this video are explained in just 4 lines. Now I can see it, but I never understood it before my journey. My journey has helped me. I hope it will help you too. Thanks again. See you in the next video.